Hey, what's up everybody? Welcome to this beginner Houdini tutorial focused on the artistic methods I use when setting up millions of particles simulations. I will explore the approaches I presented at the Houdini Users Group Sofia, and at the end, I'll quickly walk you through the scene setup for the Sans Hugs logo reveal. In addition, I'll share the project files in the description so that everyone can replicate some of the branches if they find them useful, of course. By the end of this video, I hope you'll be able to set up Drive and render your own high-quality particle simulations while enjoying the flexibility Houdini offers for motion graphics and VFX assignments. Hello guys, now when we're in Houdini, now I'm going to show you how I usually set up the basic particle advection by curve. This is my preferred approach of driving particles instead of having the basic approach with twins. Now let's create a new geometry and let's call it particles advect by curves basics. And now let's dive in. I'll create a very simple setup with two spheres and an obstacle. Let this one be the emitter geo, and I'll create another one that will be our go geo, just that we know where the particles are starting and where are they going. And let's create an obstacle in between. I'll take the pit head. Houdini has that demo geometry. Now in order to see them, we need to merge them. Now we can set the layout. This should be our go and this is our emitter. So well, let's create a very simple scene emitting particles from this emitter going that direction, aiming to the go geo. And meanwhile we're going to face some collision with the pit head. So let's start. Now the simplest way to create particles in Houdini and to simulate them is to just type pop network, which is the most simple setup that you can get. Houdini actually is going to prepare for you all the needed nodes for the simulation. All those nodes are placed inside a DOP network, but I usually prefer to start with pop, which is going to create all these nodes for me. Now when we have the pop network, we need to connect the emitter. And when we turn on the DOP network node, we're going to see some particles emitted on the sphere. Now let me connect the DOP network node to the merge so we can see all of the geometry along with the particles. Now when we've got all of the particles emitted, let's make them move. In order to move the particles from left to right, let's use pop wind, like so. Let's set the wind direction to be along the x-axis. The wind speed is the magnitude of the velocity, so basically you can play with it, animate it, and later on direct the whole animation using this kind of multipliers. At this point we don't need any turbulence or something else that distorts the motion, so I'm just going to press play and see what's going on there. As we can see, the particles are moving, but very slow, so I'll increase the wind speed, let's say to 3. That looks better for sure. Now, if you want to make the particles collide with the collision object, you need to refer somehow to it. So it's a good practice to create a null, which is going to be your reference to the collision object itself. So when we know the name of it, we can easily pick it up inside the pop network. In order to have collision objects involved in the simulation, we need a static object and we need to merge it in the main stream of the simulation. So we need a merge node as well. Let's put it inside of it. Here, it's one of the places where the order is very important. So first it should be the static object and then the pop solver. So now we need to pick the collision object. We can pick it from the choose operator and it's collision object no. When I press play, we're going to see some collision happening there. Here I'm going to show two pitfalls that's worth mentioning when you set up the collision object. Houdini actually doesn't use the exact object from the subpath, but it rather takes it and create a VDB or a volume representation of it. This is done for performance sake, so the collision process is very optimized in that way and we can gain all the speed that Houdini can provide us. So how can we see what this volume representation of the collision object looks like? It's quite easy. When you get to the collisions, RBD solver, we should first pick volume collisions, which is my preferred method for collision evaluation. And here inside, we can just turn on the collision guide. The collision guide will show you what the collision object representation in the volume grid looks like. So basically, in our case, as you can see, the volume is a little bit shrinked, and if some particles collide with the ears, they're going to stop inside next to the blue wireframe, and not as it was supposed exactly to meet the peak head's ear of the original geometry. So you have to increase the uniform division of this three-dimensional volume representation of the collider. So let's put here 100. Now, as you can see, nothing happens. That's because we have the creation frame for the static object set to 1. So basically, it's going to be evaluated just once at the beginning. This could be, of course, changed if you want the mesh to be animated, but in our case, we just need to go to first frame to see the difference. So while we're at the frame 1, we can play with the uniform division. So we can just decide the uniform division value for our interactive process and for the final simulation. That's where Houdini actually really shines, because since everything is procedural, we can start with a very low resolution for the collision, still having an idea what is going on in the scene. And then when we get to the final simulation, we can just increase this step, these divisions, and we're going to have the fine details of the collision. In our case, let's stick to 30 because the simulation is going to run really fast. Now, the second pitfall to be noticed is that the solvers, min and max substeps, actually affects the way the particles get simulated. So let's say that we have a really fast moving particles. Let's do that. Let's make a very fast particles. Let's make the particles really fly away, like 30. First, let me change the way Houdini shows the particles in the viewport. Points will be nice for small amount of particles and pixels for millions of them. Let's pick points here. As you can see, the animation doesn't look great. We can observe this pattern happening, and even worse, the particles are not even touching the collision geometry. This is due to the fact that since we have just one step in 1 second, the particles are jumping a lot of distance in that second, and they actually omit the collision itself, as well as they leave this pattern along their way. The good news is that it's a very easy fixable issue. We can just increase the number of substeps, which is going to solve that problem. Of course, this will reflect into an increased simulation time. So let's do it and see how the animation is going to change. Let's resimulate. As you can see, we're starting to get a better result. Look at the collision. It gets better than before, but still it looks a little bit away from the collision volume. So we may need some more steps. Now the things are looking better. Let's see the collision. And as you can see, the particles stick to the surface. Now we have a really nice setup of these really fast moving particles. As I mentioned before, we can drive the particles in a myriad of ways. In our case, I use pop wind as a directional force or directional wind. Inside this node, we've got some additional noise and turbulence that can be used separately or in conjunction with the wind's velocity. Along with that, we can pipe in this branch of the pop solver even more pop nodes, like pop attract, that is going to attract the particles towards goal that we set. We have a lot more of them, but the exploration of them is beyond the scope of this presentation. All these nodes share a common flow, and it's that each of them creates a simple force, and if you need to achieve a complex motion, you might need to combine several of them, which is a good approach, but when the setup gets complex, the art directing could turn into a really tedious experience. That's why I prefer not to combine myriads of pop forces, but instead I would rather prefer to create my own custom wind shaped by me. Then I use it to act as a force in the simulation to get a more predictable result. To achieve this, we need a three-dimensional structure that contains the velocities that form the wind that we need. And in our case, this should be a vector field. It's a three-dimensional structure that in each voxel of it contains a vector or a direction. When we set the custom vector field or our custom wind, we can use it to advect our particles. So how can we achieve that? We are going to use the pop advect by volumes. And the only input that this node actually has is the sub path for the volume. So let's create our custom wind. It's a geometry, so we should get back to subs. So the custom wind we are going to create is actually a volume populated with vector data. It sounds a little bit complicated, but as you're going to see now, it's very easy to set up. And the good news, since Houdini is procedural, is that you can use this setup multiple times, so we don't need to create it every single time. Before we create the volume, we need to have a geometry that we are going to transfer the velocities from. You can use different approaches, but the one that I usually use is by using curves. I prefer Bezier because I'm used to them from Illustrator and Photoshop. So let's start drawing. An important thing to note is that the order of creation of the points from which the curves are made is important because the directions of the curve depend on it. Now when we've got the curves created, I'll show you how to create a volume and populate it with the velocities that are coming from those curves. The easiest way to achieve that is to use volume velocity from curves. This node actually takes 3 inputs, but we need just 2 of them. The first one is the curves that we're going to use as a representation of our flow. The third one is the volume. It's a mandatory input that is going to be populated with the vectors or the velocities that come from the curves. So what kind of volume do we need to achieve this custom wind or this custom vector field? I usually prefer to use VDB. Our VDB is a three-dimensional structure of data and actually could contain any kind of information from color to density and, as it is in our case, a velocity. So the important difference between VDB and the other volumes is that they're very efficient in storing sparse data. It means that if you have an uneven data distribution, as in our case with the curves, the VDB is going to store only the area with sensible information around the curve and will ignore the other empty area of the volume. Now, let's define the boundaries of our field. We can use normal box geometry. Let's try to fit all of the curves neatly in it, and don't forget to leave some room for the fall off. So now when we got the area that we want our custom wind field to happen, let's create the volume itself. Now when we got the VDB as a data structure, we need to define the volume that it's going to take. We have this volume defined by the box that we have set up before. So we can use VDB activate in the fourth mode, which is reference. And we can use the second input of the node to drive the volume that we activate. So here we're going to have a volume with all of the voxels inside activated. Let me show you how you can explore the actual activated voxels inside of a cloud that you've got. We have a specific node called VDB visualize tree, and when you pipe a volume inside of it and turn on just the points of the active voxels, we're going to see a visual representation of the voxels themselves. Now all of the voxels are activated, so if you go to information, we're going to see how much voxels you use. In our case, it's like 7 million of them, so it's a quite big custom wind. How can we control the amount of voxels as a resolution? You can do that by dialing the voxel size attribute of the VDB. Of course, this could be afterwards overwritten by the other nodes that we're going to use, like the volume velocity from curves nodes. So basically, you have the volume with activated voxels. Now we can populate them with the velocity data that comes from the curve. Let's pipe the volume to volume velocity curves and see what's happening here. One thing we have missed is to name the grid inside the volume, because each voxel can contain a lot of attributes and you have to define them. They are called grids and we have to name it. In our case, let's call it velocity. The class of it is fog and the type is not float, which is just one number. We need vector float, which is a vector that shows the direction. The vector type is velocity, acceleration, displacement. Now the type of the VDB is properly set up, and here we can pick the grid that we want to populate. Now when we've got our reference volume selected, the node is going to populate our volume with the velocities coming from our curves. But how can we visualize them? The easiest way is to use the labs vector field export, since the node has this visualize option that is going to show some trails coming from the velocities in a volume. Now, how can we tweak the fall off of the velocities coming from the curves? It's very easy. You just toggle up and down the radius multiplier in the curve lookup section. And if you want to smooth the whole field, you use the smooth velocities. As mentioned before, you can change the resolution of the field by tweaking the voxel size as well. Now our vector field is ready, but there's one more step that I would suggest you to take. We have some empty areas inside the volume, and since we have activated all of the voxels inside, we're going to store the whole volume as a data, which in some cases, especially when the voxel size is really low, may have a significant memory footprint, which I suggest that we optimize a little bit. Now you can just deactivate the empty area. How can we do that? It's very simple. You just add the VDB activate one more time after the volume velocity from curves. But this time we're going to use the deactivation mode. This mode forces the node to go through all of the voxels and deactivate all of the empty ones. To visualize the outcome of this node, we can once again connect the VDB visualize tree, and as you can see, we've got 285,000 voxels, and after it we're going to have 212,000. And now we've got our custom wind fields ready to be used in the POP network. For the ease of use, I will add another node, which I'm going to reference later on in the POP network. Now we can enter the POP network and start playing with the fields. For the sake of the presentation, I'll get rid of the POP wind and pick the custom wind velocity that we have just created. As you can see, we have some move happening, but obviously the speed is not enough. So what can we do? We can just dial up the velocity scale. Let's make it 15. Alright, so now we can see how the particles are following the custom wind fields, but unfortunately they're not moving very tight to the curves. That's because the speed is very high. What we can do here is to change the advection type from update force to position. In that case, the particles are going to follow very strictly the vectors inside the vector fields. From what I see, we don't have enough particles catching up around the initial sphere. To fix that, we can do the emitter bigger. As you can see, the particles are strictly following the flow of the curves. Let's see this particular clustering. This one is due to the size of the field, of the custom wind field that we've got. Unfortunately, the lower bound is a little bit closer to the flow, and we need to add some padding here. We can fix it very easily by going to the box node, press enter, and since everything is very procedural, we're going to get all those particles updated accordingly. Perfect. Now we can play with the curves and the settings so we can achieve the effect that we are aiming for. Now starts the creative process. If we're not happy with the flow that we have in our custom fields, we can either change the bounds as we did before, or you can change, of course, the curves themselves. Now when we have created a more appealing flow of the curves, we can start tweaking the behavior a little bit. Since the simulation is really fast, you can iterate a lot. What I don't like here is that we have this swirl, which is nice, but there's some kind of very obvious border here, which I don't like. what I can do is that I can add another pop node, let's say a pop drag. Pop drag will ease the force of the particles a little bit. As you can see, the simulation is really fast, so you can iterate a lot. Now I'm happy with the overall flow of the motion. And now it's time to think about the high resolution version of our animation. What we can do is, depending on the art direction that we've got, is to decide what are the particles going to do on the micro level. So at this point, we have just a collision with the peak head, and the particles only collide with each other. What we can do is to add some more forces to further improve the motion on the micro level, or we can add some additional solvers like the grain solver that I have used for our sand example for HUGs. Since everything is procedural, we don't lose any of these behaviors. We just add up. We can just add pop grains. Pop grains is Houdini's position-based dynamic or PBD dynamic, and it handles the micro forces between the particles. But in our simple example, we can just add a little bit of turbulence. We use usually pop wind for that. We can either put it before or after the advection, and the behavior is going to change a little bit. If it's before, the turbulence is going to be advected along with the flow, which I believe looks better. In case to introduce just some turbulence, we should keep the wind velocity to 0 and just add some amplitude here in the noise, let's say 10, and see what's going on. I think that that's a lot, definitely. So let's change it to, let's say, 5, and maybe the swirl size to 0.5. Yeah, I believe that when we pump up the number of particles, this amount of turbulence and swirl size will be quite enough to get some high frequency details in the flow. Now when we're happy with the behavior, since everything is procedural, we can increase the amount of particles in the simulation. Now we have like 5,000. Let's add 2 more zeros here. I'll do the simulation. As you can see, Houdini is really fast in handling big amount of particles and is very efficient, so you can pump up these numbers really high. In order to get a better feedback, I would suggest that you go to display options by pressing D, and in the geometry tab you can set the display particles behavior. So I usually take pixels. I think the details are really nice. I think we're ready to cache out the simulation. Let's add a file cache note and just save the disk. Well, the simulation now is ready, everything's cached, and we've got the high resolution simulation of our particles. Let's check how many of them we got. Okay, at the beginning we've got like 1.5 million, and at the end of the simulation we've got like 5 million of particles. This should be dense enough so we can render a high-res render for HD. So now let's set up the lighting, the rendering, and see how we can get a pretty result out of them. Let's create a loop network. We're going to set up all of the rendering inside and have access to the Karma XPU renderer. But first, let's create another node. I'll call it scene to render. That's why we can reference that later on inside the loop network. Okay, I'll first import the geometry. I need to pick the geometry path, so We can now use the reference we've just made, scene to render. You can turn on and off the XPU or CPU render by picking one of the render engines inside WOPS. WOPS is actually a rendering environment. It's based on USD, but since this is out of the scope of this presentation, I'm just going to show you how I usually set up a simple rendering network. We first should import the geometry. Let's pick the path from the chooser. And here's the reference we've just created. Now we've got all the particles and the other objects imported. From this drop-down menu, we can choose which kind of render engine to use inside LOP. So since it is a rendering environment, you can use all the available renderers inside of it. So we can use the Karma CPU, OpenGL, or Karma XPU. My preferred renderer, of course, is Karma XPU because it's very fast. So let's pick it up. Now we can see almost interactively the rendering of 5 million particles. Now let's set up the scene a little bit further. We need a Karma renderer. Just write Karma and pipe the geometry inside. Don't forget to set the visibility to the last node. Now what we missed is, of course, the material of those geometries plus the particles, and of course we need some lighting. Let's start with the material. We can create one simple material by just adding a material library node. Inside of it we can create as many materials we want. In our case we're going to create a material X. When using Karma XPU, I would suggest you always to use material X. It's a very universal standard, so in further development of Houdini and Blender and other softwares, we're going to have a much better integration. Inside of it, we have a standard shading network. I'll pick the color of the particles. Let's pick a green color. Let's choose a more sensible name of the material. Now inside the node, we should apply the material to the geometry we want to. In our case, for simplicity, I'm going to apply the same material to all of the geometry, including the peak heads, the two balls, and the particles, of course. A very easy way to assign the materials is to just pick auto fill materials here, and then click assign to geometry. Then you just insert asterisk, which is going to apply the material to all the geometry in the network. Now we already have the material applied, and it's time to think about the camera and lighting. Let's add a camera and select it from the drop-down menu. At this point, the particles are really big. It might worth to make the radius of them smaller. How can we do that? Since the radius is a parameter that comes with geometry, we need to just add a custom attribute called pscale. The name of the attribute is pscale, and we just need to set up the value to something small, like 0, maybe 7. Get back inside and check how this radius behave. The only thing left, I believe, is adding some lights. So let's add one. Just add light to the network. I'll put the light next to the Go geometry. That way, I believe that we're going to have a nice internal shading. It's more like a galaxy or something like that. Now when we've got the focus light set on place, we can add another light. I'll change its type from point to, let's say, distant, which is just a directional light, like the sun. And we have rotated in a way that it's going to act as a kicker or a fuel light. We can, of course, put some reasonable names behind those lights. This could be the focus light, and this should be the fill light. I would say that I'm pretty happy with the results I see. Something that's worth mentioning is that if you want to have a motion blurred particles, which I really encourage you to have, because this is going to enhance a lot the rendering. In order to turn it on, you have two steps that you've got to take. The first one is to go to the object level, and here, when your geometry takes place, it's very important to go to the rendering tab here. Sampling is the second option, and pick the velocity blur option from the drop-down. That way, the renderer is going to take the velocity information from the geometry and apply it inside Karma. The second thing that you have to turn on is going to rendering, sampling, then camera effect. I would rather turn off the depth of field, but you should turn on the motion blur, and don't forget to set the velocity blur to velocity blur, and instance velocity blur to velocity blur if you want to see the velocity rendered. So that's the way you can set up the rendering of our pretty scene. Let's take a look. I like the backlit look of the particle cloud. It's like a green magic or some kind of nebula. And the good thing is that since you've got all of the particles overlapping one of each other, it acts as a volumetric rendering, like Pyro, but with a lot more details. So of course you can combine this rendering with some volumetric data, like some Pyro simulations driven by this force, of course. The speed is not that great because we're in XPU rendering, but we have chosen the CPU engine, which is kind of slow on this laptop. But when we turn it to XPU, we're going to see increased performance. By increasing the path tracing samples, we can get a more fine rendering, but it's going to take a lot more time. Well guys, now when we've seen how we drive millions of particles with this velocity field of ours, let's see what else can we do with it. Since particles are in the base of most of the solvers in Houdini, we actually can use the same vector field and the same pop approach that we have in our pop simulation to drive RBD simulations and Vellum simulation. So now let me show you how we can use it. First, let's create a test geometry. Let's start with the RBD. RBD stands for Rigid Body Dynamics, but in its core is just a particle system with attached primitives to each particle. So let's create a fracture out of this geometry. RBD material fracture is a really nice candy node that can fracture your geometry very easily in Houdini. A way to see what the fractured geometry looks like is to use the explode RBD node. So if you connect the input of the export node to the output of the RBD material fracture, you can see all of the elements spread around. You can control the fracture level from here. Let's make it 3. Now we've got enough details for the sake of the presentation. And when we're happy with the fracturing, let's add an RBD solver. And now we've got an RBD simulation. Now we've got just one force acting on our RBD simulation, and that's the gravity. And since we don't need it for the example, I'm going to turn it off. Now when I press play, nothing happens because there's no forces moving around all of these particles. So how to add forces in RBD bullet solver? You can just enter inside of it by double clicking it, and you have pretty much the same pop setup that we've got in our particle simulation, but instead piping the force nodes to the pop solver, we have an output that further connects it to the RBD solver inside of it. So basically we just need to add the same pop advect by volume node and do pretty much the same thing that we've done with the particle example. We just need to find our custom wind velocity output, set the velocity field name, and by tweaking the velocity scale we can change the amount of force that we apply to each particle and hence to each chunk of the geometry. Let's see what we've got here. Let's try to raise the velocity scale. Even now nothing happens. That's because the RBD setup in Houdini actually has a glue constraint attached by default. That's really nice because you can play around with it and have a very sophisticated simulations. But for our example, we just are going to turn it off. Now, as you can see, when all the particles gets in the field, they are getting pushed around. Now we can play with the velocity scale as well with the advection type. For this kind of simulation, I would rather prefer to use velocity update, which is going to give me a more consistent result. And since inside of the RBD bullet solver all the forces that we are connecting are just pop forces, we can just add some more of them. Let's add a pop spin, and when they both mix, we're going to see a more interesting animation with chunks spinning around and following velocity curves that we have in our custom winds. Now we know how to drive RBD simulations with our custom wind fields. Let's see how we can drive a Vellum simulation with it. Let's create a plane and rotate it so it can match the overall layout. Okay, and now what we want to do is to convert this geometry into Vellum Cloth. Vellum Cloth node. Now the geometry is a cloth that we can simulate, but first let's play with the properties of the cloth. I'll dial down the stiffness a little bit and maybe the bend so it can stretch easily. Now what we need is a Vellum solver that is going to solve the simulation. And see what happens. In its core, Vellum solver actually uses particles as well. So basically each vertex of the geometry turns to a particle and gets constrained, so it gets simulated further. And since it's still a pop inside of it, what we can do is just enter inside and add some pop forces. How can we do that? We just enter by double clicking it. So let's add pop advect by volume and do the same thing. Pick our custom wind, decide which advection type we want, and scale the forces to the point we like the motion the most. Alright, something happens. We still have the gravity, so maybe we should get rid of it. The gravity is included in the Vellum solver itself, so you can just zero it down. And now the only force that is going to act on our Vellum cloth is the custom wind that we have created. As you can see, the forces are really small for the scale, so let's make them bigger. I'll put 10 and see what's going on. Okay, that looks more interesting for sure. Once again, I'm going to use the update velocity. For cloth simulations, I would suggest you that you use the advection methods that it's more sophisticated, like trace or trace midpoint. As you can see, all of the vertices, as we mentioned, are particles, and those particles are moved by the vector fields inside the Vellum solver. And since this is Houdini, you can play with the geometry and the output of all of the solvers. Why not using the simulation to collide with the Vellum cloth? In order to do this, on the Vellum solver, the third input is the collision geometry. You can see it here. So we can just take the geometry from the bullet solver and just pipe it inside. And that way, the simulation is going to use the animated, pre-simulated RBD pieces as an obstacle for the Vellum simulation. And let's see what the result is. Now we know how you can control the most important simulations in Houdini. This is the RBD and the Vellum Cloth simulation with our custom vector fields, or custom winds as we call it. So you can drive particles in medians, you can drive fractured geometries, and you can drive different kind of cloths or soft bodies in Vellum. So now here is our simulation, and let me explain you how it's done. The heart of the whole thing, of course, is the DOP network with the pop simulation inside of it. Despite the example that we have covered in the basic setup, here we start not for a blank geometry or a start object or something that will emit particles, but instead we have already prepared volume, a geometry that contains all the sand that covers the logo and the ground. The process of populating with particles happens here in this branch. Here you can see is just a geometry that we have generated outside in a different SOP network that I have named HUGSofia. I have separated the two stages of the production. This one is just a simple geometry manipulation that takes some 3D geometry, then we put some cloth simulation on top of it, then some Boolean operations, and at the end of it, we just get this geometry, which is actually the volume that contains the particles uh, of grains that represent the scent that covers our 3D text and ground. So as you can see, nothing fancy here. It's just a cloth simulation that runs on top of the ground and the letters. And then I used some Boolean operations to extract the 3D text itself. And I have added some offset on top of that outline to represent the thick layer of sand that is covering the letters. Now, when we know where our sand should be, we can populate it with particles. That happens here in that branch. What we've got here is just we take the geometry, we scatter points inside the volume of this geometry. Then I create a custom attribute, which is a gradient, represents the y value of the particle's coordinates. It sounds complicated, but actually it just takes the y value and store it in a custom attribute. In particular, this case is the color. So we can use this gradient, this value, this attribute, to drive or to offset the advection of the scent, and it's going to look like wind starting to blow from the top layer of the scent and goes down to the ground. Afterwards, I just add some UV textures to the particles, and then I add some attribute noise of this UV, so we can have a really random color for each grains of scent. And then I just read texture of scent with these UV coordinates, and then we get all those particles ready and set up for the simulation itself. But before we enter the simulation part, the DOP network, we should create the vector fields or our custom winds. The approach here is exactly the same as the one that I have shown you in the basic example. The only difference here is that I have separated the wind field to 4 sub-wind fields because I wanted to have more control on the effect of each of the curves. So I started, of course, with the same velocity field that I have shown you, which is a VDB. Then I read the curves from an alembic because I made the curves in Blender. Then I just separate them here and create the vector fields. Out of these 4 networks, we get just 4 nodes. Let me show you the curves I have used in our particular example. I have separated them to 4 groups as I mentioned. And out of those curves, I have created the 4 vector fields I have mentioned here. Now let's get back to the simulation part. We've got the particles that are created inside the volume. Then we've got the vector fields or the custom winds that we want to blow the particles away. And we have the gradient that is going to help us to direct the review of the letters. And now let's dive in inside of the POP network. You're going to see that there's nothing different for the simulation setup. It's pretty much the same as the example I have shown you, except that instead of just one pop-out vect, I have 4 of them for each of the custom winds that I have created. That way we can play and animate the velocity scale, which is going to actually direct the way the wind blows and reveals the 3D letters. The only different thing around is that we have this pop wrangler, which is a pretty simple vex expression You're not obliged to use it, but what it does is actually that multiplies the velocity that is coming from the custom winds by the gradient that I have mentioned before. So that way, by animating those attributes here, we can redirect the review of the letters. I have added pop grains here too, so I can have these beautiful particles sticking together and clustering. And maybe the only difference here is that I have turned off the collision object since I wanted the simulation to run as fast as it can. In this particular animation, I believe that this collision is not that noticeable, so I went that way. Of course, you can turn it on, and in the cost of some more additional computation time, you're going to get a more precise simulation as well. Next, I have cached out the simulation. It doesn't play in real time because we have 50 millions of particles. This is the final production quality that I have set up. But here's a very nice trick that I use when I work with millions of particles. I reduce and create a cache. I add this Wrangler node with this custom script of mine that reduces the amount of particles coming in from the previous file cache. Then when I get the reduced cache, I can write a new cache. In our case, we got like 350,000 particles instead of 50 millions. And this is enough to get a real-time playback. So if I switch this cache instead of the other, we get this. So as you can see, now we can play in almost real time on this laptop, so it's really fast. And since the particles are really enough to give you a visual feedback of what's going on in the simulation, you can decide if it works fine. You can play with the camera and direct the whole thing. The other node that I really enjoy in Houdini is the retime node. This is so because you can post-retime things. So basically, if your particles contain velocity information, you can use the retime node to tweak the speed of the animation. So it's very simple to use it. Just animate the frame here by pressing Shift and clicking on it. We get the curve view. So since we're running really fast here, we can play a lot with the timing. And remember, since everything is procedural, when we lock the timing, you can just switch back the inputs, and now the same retiming is going to happen to the 15 millions. It works for fluids, it works for Vellum Cloth simulations, Vellum soft bodies, and for any kind of liquids and flip fluids. So for motion graphics and for fine-tuning at the final stage, and for directing the animation at the end, it's really a gem. Now, after we got everything set up, we can go to the loop network. The setup inside is nothing fancy. I load the scene. I have created several materials here, and then assigned a dome light. And as you can see, for a few minutes, by using Karma XPU, you can get this beautiful imagery that has motion blur, an environment, HDR, dome lights, and everything rendered with GI and so on. This is exactly the setup that I have used for the animation I have shown you before. So that's about it, guys. We have covered the approach that I have usually used when I set up redirectable particle scene in Houdini. It's a very robust technique, I believe, and it's a good workflow to approach any kind of complex scenes like this. It can give you a very decent result in terms of quality and render time. And of course, what's more important, you get a really nice artistic control to art direct the scene and to get exactly what you expect. All right, thank you for watching. I hope you found the video useful. Don't forget to check out the project files in the description, and always support your local community. Cheers and see you soon.